All right, so here in this video, we're going to go over a couple more properties and then briefly talk about Hermitian matrix. But in our particular case, really, we're just, since we don't deal with, not worry too much about complex numbers, we'll look at this property in relative to symmetric matrices. Right, but before that, let's add another equivalence to our NME theorem for non-singular matrices. So we can state that a square matrix is non-singular, right? If and only if. So again, an equivalence relation, right? A square matrix A is non-singular, right? If and only if lambda equals to 0 is not an eigenvalue of A. All right, and we can think of kind of the contrapositive. If lambda equals to 0 is an eigenvalue, then A is, if and only if A is singular, right? And if we approach it that way, we could say, all right, A is singular. All right, if and only if there exists a non-zero vector, right, such that AX is equal to 0. Right, that is what it means to be singular, right? Now, when this is true, right, here I can rewrite the 0 vector here as just 0 times x, right? In other words, what that means, right? And again, x is a non-zero vector. Okay, so what that means that this is true if and only if lambda equals to 0 is an eigenvalue. All right, so again, this shows that A is non-singular if and only if lambda is equal to 0. Okay, so that means that we can add another condition to our NME. So let's bring that up here. NME. So what this states here, oops. Okay, so here we go. All right, so now we can add to this. We're on round number 8 here. All right, suppose that A is a square matrix of size n. The following are equivalent. And then again, going on down to the bottom, 11 came from our previous section, and now we can add 12. Lambda equals to 0, is not an eigenvalue of A. All right, so that would mean that our matrix is non-singular. Okay. All right, now to wrap up here this part of our module, here, oops. So the size of our matrix, I guess, when we approach one of these eigenvector problems, and there is a bound to at least the size of the polynomial, right, and the number of possible eigenvalues, right? So here, theorem NEM, the number of eigenvalues. Okay, so an n by n matrix, right, has at most n distinct eigenvalues. Okay. All right, and again, that's the fundamental theorem of algebra when we're stating a polynomial, right, of nth root, right? Now that states that including multiplicities here, so it has n distinct eigenvalues, but if we add up not just the distinct eigenvalues, but add up their algebraic multiplicity, if we add those up, those will always add up to n. Okay, so this essentially just gives us a bound to the complexity of an eigenvalue problem. All right, so I know going into it, if it's 4 by 4, 5 by 5, then I'm solving a fifth degree polynomial, right? With at most 5 distinct eigenvalues, but the sum of all the algebraic multiplicities would be 5. Okay? Okay, now we didn't, and we're not really covering complex valued matrices. So when this property holds, and that A star is what's called a Hermitian matrix, but we're not worried about complex entries. So what we actually care about is symmetric matrices, which is the real value equivalent, right? So this is for complex values. We take something called the adjoint of a matrix, right? But here, these theorems still apply for real matrices, but in this case, instead of Hermitian, we just look at symmetric matrices, where the transpose is the same as the matrix A itself. All right, so as it turns out, there's a couple of nice properties that these Hermitian matrices have. Right, for one, what theorem HMRE tells me is that that every eigenvalue is a real number. Eigenvalue is a real number. Okay. Okay, and then even if the matrix is a real number, even if the matrix has complex entries, right? So even if the matrix does have complex number, its eigenvalues will be real. And then the other property, HMOE, now this states that eigenvectors of a Hermitian matrix corresponding to distinct eigenvalues. Now we know a previous theorem tells me that they're linearly independent, but this, when it's a Hermitian matrix, you can assume another property further besides linear independence. We can assume orthogonality. They are orthogonal. Okay, so now we could see why that is a desired property, right? Because now it becomes very easy to calculate some of the calculations that we we would like to do, right? So, and matrices are everywhere in applications, right? Covariance matrices in physics, you can apply a lot of these properties here, or these show up, and working with them, having calculations that involve these types of matrices are simpler calculations than if they were not. All right. Okay. So in the next section, we're going to look at a particular type of matrices and desired properties of matrices, where we're going to take a look at diagonal matrices and why they're desirable to work with.